This is section 5.5, Polynomial and Rational Functions. This is the last section of chapter 5. It's the last section of our course. Now, in 5.5, we're only going to do the polynomial functions. We're not doing the rational functions. So, polynomial functions, what are they? Definition. A polynomial function is a function that can be written as sums and or differences of different multiples of whole number powers of x. Okay, whole numbers are like 0, 1, 2, 3, 4, 5. They don't include the negatives. Okay, whole numbers don't include the negatives. Okay, we're also not allowed to put variables in the denominator with a polynomial function. So kind of loosely speaking, polynomial functions are nice functions. So, some examples of polynomial functions. Okay, number 1, all constant valued functions are polynomial functions. Remember, constant valued functions is f of x equals a number. So if you have f of x equals a number, no matter what that number is, that is a polynomial function. The power of x is x to the 0. X to the 0 power is equal to 1. And 0 is in fact a whole number. So again, f of x equals a number, that is a polynomial function. So number 2, functions like f of x equals 8x plus 11, g of x equals x squared minus 9x plus 13, h of x equals 5x to the 8th minus 6x cubed plus 11x minus 5, and so on. These are polynomial functions. I do have nothing but whole number powers on the x. Remember the power here that you don't see, it's 1. If you don't see an exponent, it's understood to be 1. So 11x, that's x to the first power. 9x, that's an x to the first power. And 8x, that's an x to the first power. And again, remember, all numbers are polynomials. Okay, we can look at examples of things that aren't polynomial functions. So the following are not polynomial functions. And we'll also state why. So our first one. F of x equals x to the minus 2. Okay, the minus sign got slightly eaten up by the variable, but that's x to the minus 2. Okay, the reason it's not a polynomial function, you are not allowed to have negative exponent on variables. So polynomials do not allow negative exponents on variables. It's okay if you have a negative exponent on a number, but you're not allowed to have a negative exponent on the variables. For polynomial functions, all the restrictions are on the variables, not the numbers. Because all numbers, no matter what the number is, that's a polynomial function. Number 2. G of x equals 4x to the 2/3. Okay, 2/3 is not a whole number. You're not allowed to have fractional exponents on variables. So fractional exponents are not allowed on variables with a polynomial function. Again, the restrictions are on the variables. Number 3. I have h of x equals x over x plus 1. Now, even though the exponents are 1, again, because we don't see them, you're not allowed to have a variable in the denominator. So polynomial functions do not allow variables in the denominator. So again, no negative exponents on variables. No fractional exponents on variables. No variables in the denominator. Those are the restrictions for polynomial functions. There's actually one other that we don't really concern ourselves with, but you're not allowed to have variables with a radical. You're not allowed to have variables with absolute values. Again, all the restrictions are on the variables. No restrictions on the numbers. So no negative exponents on variables. No fractional exponents on variables. No variables in the denominator. No variables can be part of a radical, like square root, cube root. No variables can be inside of absolute values. So it's kind of like the horrible things that can happen to functions. We just don't allow them anymore. Terminology for polynomial functions. Number 1, the largest exponent on a variable in a polynomial function is called the degree of the polynomial function. If there are no variables, like f of x equals a number, then the degree is 0 with one exception. So all numbers with one exception have degree 0. The exception is the degree of f of x equals 0 does not exist. So all numbers except for the number 0 have degree 0. And the number 0 itself its degree does not exist. But other than that, the degree of a polynomial function is the largest exponent on a variable. Number 2, the numbers that multiply the variables are called the coefficients of the function. Like if you have 3x squared, the coefficient is 3. And the degree would be 2, of course, 3x squared. Number 3, the expressions between the plus and minus signs in the function are called the terms of the polynomial function. Now, the minus sign does belong to the term that's to its right. For example, if I have f of x equals x minus 5, the minus sign does belong to the 5. So again, remember, the minus sign belongs to the term to its right. Like f of x equals x minus 5, the minus sign belongs to the 5. Number 4, the leading term of the polynomial function is the term that has the largest exponent on the variable. Now remember, the largest exponent of the variable is the degree. So basically the leading term is the term that gives the polynomial its degree. Now if the polynomial is written in correct order, the leading term usually is the very first term, but it doesn't have to be. The leading term is simply the term that has the largest exponent on the variable. Number 5, the leading coefficient of the polynomial function is the coefficient of the leading term. Remember, the leading coefficient, that is just a number. The leading coefficient must exist. The leading coefficient cannot be 0. Remember, the leading term, it contains the coefficient, the variable, and the exponent on the variable. The leading coefficient is simply the number that's multiplying the variable part. And again, the leading coefficient must exist, and it cannot be 0. And lastly, number 6, the constant term, or constant coefficient, or simply the constant of the polynomial function, is the term that does not have a variable with it. If all the terms have a variable, then the constant term is 0. The constant term, again, always exists, just like the leading term, the leading coefficient. So again, the constant term is the term that does not have a variable. And if all of the terms have a variable, then the constant term is 0. For example, f of x equals x. The constant term is 0, because f of x is the same thing as f of x equals x plus 0. So remember, constant term has no variable, and if all terms have a variable, the constant term is 0. Constant term must exist. Leading coefficient must exist. Leading coefficient is not allowed to be 0. Leading term must exist. Let's try some examples of all this. So for each of the following, we're going to, in part A, list the terms. In part B, we're going to find the degree. In part C, find the leading term. Part D, find the leading coefficient. And in part E, find the constant term, and of course we will simplify all our answers. Okay, here's our first example. F of x equals 3x squared minus 9x plus 5. Okay, our solutions. Remember, the terms, they're the stuff between the plus and minus sign, and the minus sign belongs to the term to its right. So our terms are 3x squared minus 9x and 5. So those are the terms. 3x squared minus 9x and 5. Okay, in part B, we're supposed to find the degree. Remember, the degree is the largest exponent on a variable. The largest exponent on a variable is 2. So our degree is equal to 2. part C, we're supposed to find the leading term. Okay, the leading term is the term that has the largest exponent on a variable. Here are terms. The largest exponent on a variable is 2, so the leading term is 3x squared. Leading term equals 3x squared. Okay, part D, the leading coefficient. Okay, the leading coefficient is the coefficient of the leading term. Okay, again, here's our leading term. Its coefficient is 3. Our leading coefficient is equal to 3. Okay, and then part E, find the constant term. Remember, the constant term is the term that does not have a variable. Okay, the term without a variable is 5. So our constant term is 5. Okay, example number 2. G of x is equal to x minus 44. Okay, doing the same things again. So our solutions. Okay, again, list the terms. There's only 2 of them. So our terms are x and negative 44. Okay, in part B, we're looking for the degree. Okay, the degree is the largest exponent on a variable. Okay, remember, you don't see an exponent, so it's understood to be 1. So our degree is equal to 1. Okay, for part C, we're supposed to find the leading term. Okay, the leading term is the term that has the largest exponent on the variable. Okay, this is the only term with a variable, and its exponent again is 1, so that is the largest exponent. So the leading term is equal to x. The leading coefficient is supposed to be the coefficient of the leading term. Again, the leading term is x. The coefficient that you don't see is 1. Remember, it's 1 times x. So our leading coefficient is equal to 1. And then for part E, the constant term, okay, the term that does not have a variable, negative 44. Our constant term is negative 44. Remember, that minus sign does belong to 44. Don't lose it. Okay, example number 3. H of x is equal to negative x to the 7th power. Okay, doing the same 5 things again. Okay, so our solutions. Okay, we're supposed to list the terms. There is only one term. So the terms are just negative x to the 7th power. Okay, and then in part B, the degree. Okay, the degree is the largest exponent on a variable. The largest exponent on a variable is 7. So our degree equals 7. Part C, the leading term. Okay, there is only one term. So the leading term is negative x to the 7th power. The leading coefficient is supposed to be the coefficient of the leading term. Okay, again, the leading term is negative x to the 7th power. Okay, that negative really means negative 1 times x to the 7th. So our leading coefficient is equal to negative 1. And lastly, the constant term. Okay, the constant term is supposed to be the term that does not have a variable. Okay, there's only one term and it has a variable. So remember, when that happens, that all the terms have a variable, the constant term is equal to 0. Now we've got one more of these. Number 4. K of x is equal to 11. Remember, function equal to number, that's a polynomial. So our solution is supposed to list the terms. Well, there's only one term, 11. So the terms, just 11. Okay, for part B, the degree. Remember, all numbers, except for 0, have degree 0. So this number isn't 0, so its degree is equal to 0. Supposed to find the leading term? Well, again, there's only one term, so the leading term has to be 11. Okay, leading coefficient. Okay, when it's a constant term, the leading term and the leading coefficient are the same. So the leading coefficient is also 11. That always happens with a constant valued function, that the leading term and the leading coefficient are the same. The constant term, it's also 11. It's the only thing we see, 11. So for constant valued functions, leading term, leading coefficient, constant term, and all the terms are the same. a look at some special polynomial functions. Special in that they have their own special names. So special polynomial functions. We've actually already used a few of these names in some of our regression models. So polynomials are usually grouped by their degrees. The degree actually, even though it's easy to find, the degree tells us how much the polynomial wiggles if you graph it. So the degree of a polynomial function gives the polynomial its name and determines the general shape of its graph. So we're going to give a table that summarizes these properties. So the special name polynomial function will have its degree, the form, its generic form, the actual name that it has, its specific name other than polynomial function, and what does its graph look like. Okay, you might need a little extra room than I have here between the degree, its form, and its name. The form can sometimes get to be very, very long. The name's not long, but the form can be incredibly long. So for degree 0, it's f of x equals c. F of x equals a number. The name is constant. Its graph is a horizontal line. So again, c is just a number. So f of x equals a number. It's called a constant. It's a horizontal line. Degree is 0. So degree 0 is a special case of degree 1. So degree 1 looks like f of x equals mx plus b. It's linear. It graphs as a line that's not horizontal. It's also not vertical. So a line that's not horizontal or vertical, it's sometimes called oblique or a slant line. But anyway, that's degree 1. And we've done linear regression. Okay, degree 2 looks like f of x equals ax squared plus bx plus c. It's called quadratic. It graphs as a parabola. Okay, a parabola is that kind of U-shaped looking thing, or a U-shaped upside down. The next degree, degree 3. The form is f of x equals ax cubed plus bx squared plus cx plus d. It's called a cubic. The graph is what's called sigmoid shaped, kind of S-shaped. Sometimes you have to use your imagination to actually see the S, but it's kind of like it's doing something like this, or the upside down version of that, something like that. Notice if you do something like this, you actually do have two relative extrema, a relative max and a relative min. Anyway, that's the cubic, ax cubed plus bx squared plus cx plus d. Degree 4. It looks like f of x equals ax to the 4th plus bx cubed plus cx squared plus dx plus c. It's called quartic. Quad is also a prefix for 4, even though it applies to degree 2 polynomial. So since quad was taken, we had to go to the other prefix for 4, quartic. The graphs, a w, an m, a u, or a u upside down. It's just a coincidence that it's degree 4 with 4 possible shapes, because if you think about it, an m is a w upside down. So it's really only 2 basic shapes. Notice if you do a W or an M, you would actually have 3 relative extrema. The U's and the U's upside down only have 1 relative extrema. That is sometimes why we do polynomial regression, is that we actually have more than 1 relative extrema based upon the way the points plot. And the last degree that we look at that has a name is degree 5. It looks like f of x equals ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus ex plus f. The name is called quintic. And what does the graph look like? They're simply too numerous to mention. Generally speaking, their graphs look like a mess. Okay, they're just very, very messy looking. So again, those are our specific names for certain types of polynomial functions. And again, it's based upon their degrees. And if you know your prefixes, with the exception of degree 2, they do kind of make sense. The degree 2, the prefix for a 4, doesn't quite make sense to us anymore. Let's try some examples to see if we can remember these names. Now, when we start doing regression, again, we've already done the linear. You'll actually see something that says quad regression, Q-U-A-D-R-E-G, cubic regression, C-U-B-I-C-R-E-G, quartic, Q-A-R-T-I-C-R-E-G. They don't have the quintic. So, examples. Give the name of each of the following functions or state that the function is not a polynomial function. Here's our first one. I have f of x equal 3/4. Okay, it's a number. Okay, f of x equals a number. Remember, those are constant or constant valued. So our solution, it's a constant. Okay. Remember, f of x equals a number is always a constant. The degree would be 0. Okay, number 2. I have g of x equals 5x to the 4th minus 8x squared plus 8. Okay, again, look for the largest exponent on a variable. It's 4. Okay, it's 4th degree, so its name is quartic. So this is a quartic polynomial. Number 3. I have h of x equals x to the 5th minus 9x squared plus 13x plus 11, all over 17. So let's see our solution. Okay, remember, it's okay to have a number in the denominator. So this is a polynomial. Okay, it's okay to have a number. You just can't have a variable in the denominator. So since it is a polynomial, you look for the largest exponent on a variable. It's 5. So degree 5 is quintic. Number 4, I have k of x equals x minus 3x squared plus 14. Okay, it appears to be out of order, but the largest exponent on a variable is 2. Okay, that's the largest exponent on a variable, so it's 2nd degree, which makes it quadratic. Okay, scrambling up the order does not change the name. And then number 5, I have p of x equals x minus 8 to the 5th power. So our solution. Okay, the largest exponent on a variable is 1. This 5, that's exponent of 5, that's on a number. That doesn't matter. So this is a 1st degree polynomial function, which makes it linear. Remember, it's the exponent on the variable, not the exponents on the number that matter. Okay, let's do some regression. So polynomial regression. Okay, there may be physical reasons or in the applications of why you would want to do a polynomial regression, even if it is not the best fit for the data. So the most compelling reason is you want a certain number of relative extrema. It's kind of like when you plot the data, it appears to make an S, that would be sigmoid, that would be cubic. Or it appears to make that parabola, then that would make it quadratic. Okay, now, most polynomials have more than one extrema, provided their degree is bigger than 2. So we have this little theorem. A polynomial function of degree n can have at most n minus 1 relative extrema. So notice degree 2 can have only 2 minus 1, or only 1 relative extrema. Degree 3, 3 minus 1, it can have 2. Degree 4, 4 minus 1 is 3, it can have 3. So that means if you have a cubic polynomial function, again, n is 3, there will be at most 3 minus 1, which is 2 relative extrema. Kind of, you could have a max, you could have a min. And sometimes the data seem to support that. Now, in the absence of any compelling reasons, we will use the polynomial function that best fits the data. So there actually is a test to determine what degree polynomial function is the best fit for the data. And it's an analytical method as opposed to, you plot the points and say, oh, it looks like a S, it looks like a W. So theorem, given data that have uniform independent variable values, which means all the x values are the same distance apart, if the nth differences are all equal or approximately equal, then a polynomial function of degree n is the best regression model for the data. Furthermore, if the nth differences are all exactly equal, then there exists a polynomial function of degree n that will exactly fit the data. I used the word exactly too many times, didn't I? So you just look at the nth differences. If they're equal or about equal, you want an nth degree polynomial. Now again, if you think about how we calculate differences, so again, think about how we calculate differences, if the nth differences are all equal, then the next differences, called the n plus first differences, they would all be 0. So our corollary, given data that have uniform independent variable values, if the n plus first differences are all 0, or approximately 0, then a polynomial function of degree n is the best regression model for the data. Furthermore, if the n plus first differences are all exactly 0, then there exists a polynomial function of degree n that will fit the data exactly. So again, you just calculate differences. And as soon as you can see that the differences are all equal or approximately equal, then you know the degree of the polynomial function that will fit them. I guess I should say fit them the best. Now, just like when we were doing linear regression, it was exactly linear or approximately linear. The same idea applies here. It could be exactly quadratic or approximately or almost quadratic. So if all the second differences are exactly equal, it's exactly quadratic. If all the second differences are almost equal, it's almost quadratic. I'm going to try a couple of examples. So, examples. For each of the following, in part A, we will determine what degree polynomial function is the best regression model. Because unless we're told, we have to figure out which regression we're going to be doing. Part B, find the regression model. If necessary, round parameters to 3, place to the right of the decimal point. Question C, is the data exactly or approximately an nth degree polynomial? And question D, graph the model and the data in an appropriate viewing window. Now, if it's given to us in a table, the table can help us with the appropriate viewing window. Now, sometimes the window may not be large enough for us to actually see an S-shaped or a W-shaped and so on like that. So we're going to find the degree, the model, determine it's exactly or approximate, and then graph. Here's our first one. My x's are 1, 2, 3, 4, 5, 6. My y's negative 26, negative 42, negative 48, negative 32, 18, and 114. Here are solutions. Okay, hopefully you do observe that the x's are uniform. They're all 1 apart. So our delta x is equal to 1. Okay, the delta x is equal to 1 for every single one of them. So we calculate some differences. Remember, the differences when we look at the y's. So let me reproduce the y's. The negative 26, negative 42, negative 48, negative 32, 18, 114. Okay, those are my y's. Remember, when you do the differences, it's right minus left. Okay, right minus left. So I'm doing negative 42 minus negative 26. I got negative 16. Negative 48 minus negative 42. I got negative 6. Negative 32 minus negative 48. I got 16. 18 minus negative 32, 50. And 114 minus 18, I get 96. So far, I would say that these are not equal, and they're not really close to each other either. The 96 seems to be way out there. So it's not linear. Okay, the second differences. So you're going to do right minus left. So negative 6 minus negative 16, 10. 16 minus negative 6, 22. 50 minus 16 is 34. And 96 minus 50 is 46. They're still not equal, and they're not even approximately equal. Because 10 and 46 kind of far apart there. So that was our second differences. So now we've ruled out quadratic. So now we calculate the third differences. Again, remember, it's right minus left. 22 minus 10 is 12. 34 minus 22 is 12. 46 minus 34 is 12. These are all the same. So all of the third differences are exactly equal. So you can start answering the questions. Part A, third differences are all equal. The best model is a degree 3 or cubic. We will be doing cubic regression. Okay, for part B, the actual regression. Okay, we don't need to worry about round off because, again, they're all exactly equal. So let's see. Remember, we put the x's in list 1, the y's in list 2. So if I take out my calculator, okay, make sure my lists are empty. Second memory, choice 4, I've cleared out my list. Okay. Now remember, since we're going to be graphing, I'm going to store my regression equation in L1. So stat, edit, we're going to, so let's see, they went 1, 2, 3, 4, 5, 6. 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, 6, enter. Now again, be very careful, be sure you enter them correctly. I can't see my y1, it's negative 26. Then negative 42. Okay, let me go back. Negative 48, enter. Negative 32, enter. 18, enter. 114, enter. Okay, I got them all in. So we'll quit that. We stat, scroll over to calc, and you're looking for cubic. It's choice number 6. Okay, cubic regression. Notice there's quad, there's quartic. Notice there is no quintic. So got to scroll down to my cubic, or you can just press 6 from the keypad, and we're going to store it in y1. So let's scroll down to there. Bars, y bars. Hopefully we've done this enough times that it's just something routine for you now. Then calculate, and there it is. So it looks like when I have 2x cubed minus 7x squared minus 9x minus 12. So let me get caught up here on my slides. So there. And there's your model. Y equals 2x cubed minus 7x squared minus 9x minus 12. Now again, if you cannot store the regression equation in your y1, you would key that into your y1. Remember, it was exact. So that was what, question C. Since all of the third differences were exactly equal, remember they're all 12, the data are exactly cubic. And then, oh, I've got to turn on my stat plots, right, if I want to see the data. So our calculator, there it is. Let's quit that. Second stat plot. Turn on second stat plot. Turn on number 1. Did you notice when I did my y equal that it didn't exactly say 2, it was like 1.9999 and so on? But let's see, let's set our window. Okay, let's set our window. Okay, if I get my window, I get my window from the data. Okay, the x's go from 1 to 6, so I believe window 0 for a minimum. Just a smidge further, let's go to 7. Scale of 1, sure, why not? Okay, now notice our smallest y value is negative 48, so I'm going to go down to negative 50, and my biggest one is 114, so maybe 120. So let's see, negative 50, a max of 120, and being that far apart, I think I'll have a scale of 10. And let's graph. Okay, so there's our regression model. Did I not turn my stat plots on? I don't see the dots. Second stat plot. I didn't turn it on. I said I was going to, but I didn't. Now I've turned it on. There. And remember, since it was exact, it is supposed to go through them. And it does. Okay? The little squares got filled in. So, there we are again. I can remember my window was 0, 10, 1 by negative 51, 20, 10. Okay, I went out to 10 instead of 7 like I did on my calculator here. So something looks like that. And in case that one wasn't enough fun for you, I got a second one. So here are my x's, 2, 4, 6, 8, 10, 12. Notice they are uniform. My y's, negative 13, negative 18, negative 14, 1, 25, 59. So since while you guys write that down, let me get my calculator set up again. Okay, clear that out. 7, quit. Clear out my list. Second memory, choice 4. Clear all list. There. Oh, well, since I know I'm going to be graphing it, let's go ahead and put in the data. Oh, I don't know the regression yet, do I? Well, I can still put in the data. So stat, edit, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. Again, I just don't know which model I'm going to be using yet. So let's see, my y's. Negative 13. Negative 18, negative 14, 1, 25, 59. Okay, I believe I can also set up my windows. Notice my largest value of x is 59, so I might go out to 60. And for this one, I don't know, I want to keep my origin in the middle, so I'm going to do negative 60 to 60 on y, but for x, maybe 0 to 14. So window 0, 14, increments of 2, and then to put my origin in the middle, so negative 60 to 60. Again, it was just to put my origin in the middle. 10 sounds good, so let's quit that. Okay, now let's do the work to figure out what regression model am I using. So first of all, our solutions. Okay, for part A, we do notice that the delta x is 2. So we can calculate differences. So I'm going to reproduce the y row, the negative 13, negative 18, negative 14, 1, 25, and 59. Again, then we start calculating our differences. Remember, it's right minus left. So negative 18 minus negative 13 is negative 5. Negative 14 minus negative 18 is 4. 1 minus negative 14 is 15. 25 minus 1 is 24. 59 minus 25 is 34. Well, they're definitely not equal, nor are they even close to each other. So that rules out linear. Remember, it probably wouldn't be linear in chapter 5 since we already did linear. So you should expect at least go to the second differences. So let's calculate those second differences. Again, right minus left. 4 minus negative 5 is 9. 15 minus 4 is 9. 24 minus 15 is 9. 34 minus 24 is 10. Notice they are approximately equal. So this is going to be approximately quadratic. So the second differences are almost equal. So the regression polynomial should be degree 2, which would be quadratic. Now, because it's not exact, I'm going to set my float to 3. Remember, if necessary, we're supposed to round to 3 places. So mode, let's float on over to 3. Enter. And we quit that. And we now know we're doing quadratic. So stat, calc, we look for quadratic, choice 5. And since we're going to graph, we'll put it in y1, bars, y bars, function, enter. And we calculate. So we're going to have 1.228x squared minus 9.987x plus 2.100. So let's get caught up here. So there's our regression equation. Y equals 1.228x squared minus 9.987x plus 2.100. Remember, for part C, the second differences were not exactly equal, they were approximately equal, so this is approximately or almost quadratic. So for part C, it's approximately quadratic. And for part D, except I've got my windows set up and everything, so if I take out my calculator, remember my windows were 0, 14, 2 by negative 60, 60, 10, so graph. And there we go. Now, of course, we can ask all the kinds of questions we look at when you look at the graph. You know, it is concave up. It's decreasing until you get to x equals. Remember, these are multiples of 2, so 0, 2, 4 until you get to 4. Then it's increasing from 4 on out. So all the things that we can ask about graphs, we can ask about them here. So to make it official, that's the end of section 5.5. It's the end of chapter 5. It's the end of the material for the course. So they all lived happily ever after.